When we solve systems of linear equations, we are essentially hunting for a single point of agreement. We are looking for the exact node where multiple independent planes intersect in space. This graph shows two linear equations plotted against each other. When we only have two variables, solving the system is as simple as drawing lines and finding their physical intercept, right where x1 is 4 and x2 is 3. But this visual intuition has a hard physical limit. Once a system expands beyond 3 variables, we run out of dimensions to map. We cannot draw a 4-dimensional intersection. To find these intersections without drawing them, mathematicians rely on algebraic determinants. A determinant is a single numerical value extracted from a matrix of coefficients that defines the geometry of the system. Drawing graphs and solving tiny matrices works perfectly for textbook examples. Real-world engineering, however, requires balancing thousands of interacting variables simultaneously, demanding a completely different approach to the math. The standard analytical method for solving these algebraic systems without graphing is known as Cramer's Rule. Cramer's Rule isolates each unknown variable by setting up a fraction. It takes the determinant of a modified matrix and divides it by the determinant of the main coefficient matrix. The structural weakness of this method becomes obvious when we look at the arithmetic required just to expand a basic 3x3 matrix. The calculation fractures into multiple 2x2 determinants, cascading into a long string of multiplication and subtraction. Now apply that same cascading formula to a massive modern matrix, say 1,000 by 1,000 variables. The sheer number of multiplied terms scales factorially. Resolving it requires an impossible amount of processing weight. To process massive systems, analytical fractions are a dead end. We have to discard formulas like Cramer's Rule entirely and adopt a step-by-step mechanical algorithm. That mechanical algorithm is Gauss Elimination. It is a 2-phase sequential process explicitly designed for machine execution. Phase 1 is forward elimination. The algorithm subtracts multiples of rows from those below, carving out the bottom left. It eliminates coefficients until an upper triangular form remains, leaving zeros below the diagonal. Phase 2 is back substitution, working from the bottom up. This specific triangular structure is required because it guarantees isolation. As the algorithm moves up the rows, it only ever faces one unknown variable at a time. Gauss elimination transforms a chaotic web of simultaneous relationships into a predictable, orderly cascade. Here is the starting state for a standard 3x3 system: initial coefficients on the left, target vector on the right. The algorithm executes the first elementary operation, using the top row to surgically eliminate the second row's first coefficient, turning it into a 0. This loop continues until all necessary coefficients below the diagonal are zeroed out, completing the upper triangular form. Now, back substitution begins. The bottom row is the simplest equation. 3 times x3 equals -3, meaning x3 is -1. From there, the upward cascade is automatic. We plug that -1 into the second row to find x2, and then plug both values into the top row to find x1, giving us a final solution vector of 2, 1, and -1. Because this entire method relies entirely on predictable, repetitive arithmetic loops, it perfectly translates human math into executable machine code. When we write these steps into software, the basic implementation is known technically as naive Gauss elimination. This script shows how those mathematical steps translate directly into nested computational loops. Notice the 4k and 4i loops driving the forward elimination phase. Every time those loops run, the computer performs basic math. We measure this effort in floating point operations, or flops. Flops are the strict metric used to calculate exactly how much time an algorithm will cost a processor. The computational cost of Gauss elimination scales cubically. This is mathematically expressed as an O of n cubed flop count. As the matrix grows, the time required to process the forward elimination phase curves upward aggressively. While naive Gauss solves the analytical scaling problem that broke Cramer's Rule, its cubic growth means giant matrices will eventually choke standard processors. To go bigger, we have to look for structural optimizations. The naive algorithm has a critical flaw. It assumes perfect arithmetic and ignores the physical limitations of computer processing. The primary failure state occurs if a coefficient along the main diagonal happens to be exactly 0. the algorithm will attempt a division by zero, and the calculation will catastrophically crash. There is also a secondary, more insidious failure state. If the computer tries to divide by a number incredibly close to zero, it generates round-off errors that compound and corrupt the final result. To stabilize the code, we have to introduce an algorithmic patch called partial pivoting. When the system hits a weak diagonal element, it pauses. It scans the column below for the largest absolute value and physically swaps the rows to put the strongest number in the pivot position. Partial pivoting provides the essential bridge between pure algebraic theory and the messy, error-prone reality of digital computation. Even with stability patched, we still face that massive O of n cubed flop cost. For incredibly large engineering models, a stable algorithm still takes too long if it has to process every single number. The solution is to exploit the matrix topology. This means recognizing when a dataset naturally forms a localized pattern, known as a banded structure. A specific example is a tridiagonal system. This is a matrix with a bandwidth of exactly 3, meaning all the meaningful data sits on the central diagonal and its immediate left and right neighbors. Everything else is simply 0. Running the standard naive Gauss algorithm on a tridiagonal system is immensely inefficient. The processor will waste millions of cycles doing heavy arithmetic on empty zeros. Instead, programmers use a customized tridiagonal solver designed to explicitly target this exact sparse stricture. Because it only processes the active bands, it removes heavy nested loops, collapsing that massive O of n cubed effort into a single computational pass. Computational mastery aligns the architecture of an algorithm with the physical topology of the data.